Good morning, everyone. Myself, Neeraj Bhardwaj, and I'm faculty of geography at Drishti IAS. And today we are going to start a session, a new batch for this particular examination, that is Uttar Pradesh Assistant Professor exam. This exam, as we know, the geography subject plays a very important role and it has a very high success also in this exam. And since most of you and all of you have come from the geography background only few candidate opt geography in the latter stage. Otherwise, I am very sure that you have studied geography at class 10th level, 11th, 12th level, graduation, post-graduation. Thus, you people have a very good understanding also. But as we know that if you have to qualify any exam, you need to have a particular good strategy. It is not only the content that matters, it is also the art of handling the content as well as how you approach to the question paper. How do you approach to the options they have given to you? The type of question you will find in MCQs, it is pretty sure that they are going to give you the 4 options. Till date, the pattern has not changed, thankfully. A question is, and the 4 options are, you have to tick the question. The kind of difficulty they can come with, that they will give you the sets that consider the following statements, or the other type of questions. If you have gone through the paper of UPPCS or UPSC examination, they have not given this kind of thing. So it is a very win-win situation for the candidate, that the simple topic we have to cover, and we have to solve the questions, we have to frame the question and solve the questions, as well as we have to cover the PYQs. Now, before we start this session, since it is the very first class, I want to give you the modus operandi. How are we going to cover this entire syllabus? You know that there are 10 units, and each unit has almost equal weightage. Starting from the very first thing, and that is geomorphology. Geomorphology, climatology, and oceanography. If we take these 3 units along with environmental and biogeography, then very simply we see that the equal weightage is there. Every year from this part, each section has around 5 to 6 on an average, we can say. Fine, I am taking broadly 5 to 6 question. It means some sets are there, some years are there when the question is 3 to 4 from 1 or 2 topic, and from the rest it is 1 or no question. Like if the cycle of erosion is there, so from the cycle of erosion, sometimes they have asked the question, they have not asked the question. But the endogenic, exogenic forces, you will find that almost every year question is there. Similarly, in climatology, they have asked the question from the climatic classification. They have asked from the chemical composition of the atmosphere. They have asked about the temperature and the pressure belts. Fine, permanent winds are there, local winds are there. So this way they have asked the question. Either it concentrates into certain area and the 2 to 3 questions are from that part, or equal distribution is there. Some year they do not ask any question from certain topic. So if we follow this pattern, then we find that From this part, there is around 7 to 8 question, 5 to 6, 5 to 6. And the 7 to 8 question I said because the two aspects are added into this, environmental geography and the biogeography. So it means if we this way, if we carry on in the human geography, if we enter into Indian geography, and thereafter we enter into the cartography. Cartography. Then in cartography, like the GIS is there, simple mapping technique is there. Almost everywhere you will find the same pattern. 2 to 3 question, 4 question. Thus, we cannot make a trend that from this part more number of questions are there. That is why we should give emphasis on this part, and the other parts we can simply neglect. No, this is not going to happen. Usually we do to crack competitive examinations. Fine, this pattern is followed to crack competitive examinations, but this competitive examination is not like that. We have to approach each and every unit very substantially. Secondly, we find that certain years are there. In those years, not only the question pattern has little changed, but also they have asked the question numerical based, especially from the cartography part. Numerical based matlab, numerical based means when we say that if any topic has some figure, say for example, if the mapping is there, so on that mapping part they have asked that what would be the measurement of this. Fine, what would be the right way to depict this particular feature on the map? What would be the scale of that? How will you derive that scale? Why this scale is being used, or which scale would be the most appropriate scale to depict some things on the map? So there are some numerical based also. However, these are not difficult questions. Very easily, just by applying our logic. Fine. Even many a times without any calculation, we can find out the correct answer. So this is the approach. Now, the entire syllabus, if we say, so we will go topic by topic. I hope that you people have that syllabus. Fine. You can see that what topics are there in each and every unit. We will go by that without skipping any one of them. Thirdly, that to qualify how many number of questions we need to answer. This is something, it depends upon, that if you are scoring as high as possible, it is always a right strategy, because you do not know exactly that what would be the final limit above which the candidates will be called for, or other students will not be. So my idea is there, my strategy is there, that instead of thinking about that how many number of questions should be given as a correct answer, we should think about covering the entire syllabus in a very comprehensive way, every topic in a comprehensive way. Now, one topic or the two would be very convenient topic for one candidate, and the same topic could be very difficult for the other. तो ये सोचना कि हम केवल एक टॉपिक को करें और यहीं से आए, तो it is possible obviously that the few candidates will not be comfortable with that. So if we make the strategy that this and this we should do and the others we should skip because we have to score this much of only, it is not a very right strategy according to us. Thus, we will be covering each and every topic, and I'm very sure that I will make you comfortable on each and every one. Today, we are going to start with geomorphology. 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 Syllabus you have seen, I'm sure. But let me simplify it. because many a times the language they use, it is bit confusing. And if you analyze the question paper they have given you in the past, we find that the following topics are there in this unit that need to be covered. It is Earth's interior, continental drift theory, plate tectonics, endogenic forces, and exogenic forces, volcanism, earthquake, cycle of erosion, isostasy, and landforms developed by river, wind, glaciers, coastal waves, and groundwater. This is the topic. Now, when we talk about the endogenic forces, then here we cover mountain building also. Fine. Mountains, their types, plateaus. Fine. And the exogenic forces are there. Exogenic forces are, these are responsible for, we can say, like uh, all relic mountains, highlands after erosion, fine, and plains through erosion and deposition, fine, or we can say denudation activities. Why this kind of explanation of the syllabus is needed? That few questions you will find in some years you can easily answer if you have the better understanding of the syllabus itself. It does not require a very deep knowledge. Fine. Say, for example, they have asked in 2023 that which of the following landform is developed due to tectonic activity. All right. Now, they have given four options. Three of them are from this part. One is developed by glacier, other is developed by wind, other is developed by groundwater. And the fourth one is there, that is about the fault. So, if you have the clarity that which one is coming from the endogenic, which one is coming from the exogenic, how these agents work on the Earth's surface to develop various types of landforms, so things start becoming easy. So, what we will do, we will go this way, one by one. All right, and that would be very convenient situation, comfortable situation for all of you. If you need something else to do, then apart from the class, however, I will cover each and everything. You do not need to depend upon the other sources, but I will suggest you that whatever the coverage we are making here in the class, whichever the traditional or conventional book you people have, you can make the use of that. Fine. Like for the geomorphology, you can make the use of Savindra Singh geomorphology. According to the exam, fine. According to the question they have asked, this one book is sufficient. You do not need to go for the other books like the Stroller and Stroller. Fine. A number of books you can keep on increasing. It is up to you. But the idea is that study one book 10 times instead of studying 10 books one time. Fine. And my class will be very, very comprehensive. You will get almost all the questions what they have asked or what they will be asking from my class. But for the safer side, I am suggesting you to just go to the Savindra Singh Geomorphology, and I'm very sure that all of you have this book with you. So let us start with the first chapter, and that is Earth's interior. Earth's interior. First of all, you see that what kind of question they ask from the Earth's interior. They will ask you about the different limits. They will ask you about the different properties, which are the different methods to know about the interior, and how do each and every method work, up to which extent these are responsible for sharing information about the Earth's interior, and so on. Fine. So we will go with this. When we talk about Earth's interior, and this is our Earth, in the very middle, we have the core or the center. The idea is that we have to get the information about this much of distance, either from this side or from this side or from this side. Fine. And the distance from the surface to this is the surface. This is surface. Fine. This is radius, and this is the core. So from here to here, the distance is 6370 kilometer. So idea is that up to the depth of 6370 kilometer, what kind of behavior Earth interior has? Fine. When we talk about the behavior, behavior of interior, so there we are trying to witness that what temperature it has, what density it has, what amount of pressure it has. Fine. Then which state it is? A state of rocks. And a state of rocks means is it solid or it is liquid. Fine. And finally the properties of each layer. Properties of each layer. Layer in the sense that we know that in the central part this is the core, and thereafter there is the other layer, and that is the outer core. Thereafter it is the mantle part, and thereafter it is the crustal part. Fine. So we can say that 1, 2, 3, 3, and 4. 4 basic layers are there. That is inner core, outer core, mantle, and the crust. The very simple, and or we can say the first question which comes into our mind, it also suggests that if there are the layers, how do we know about this? Means where from we got the information that there are the layers in the Earth's interior. It means that the Earth interior is not a homogeneous body. That we will investigate, we will understand one by one. Now, the very first thing is that since the distance is 6370 kilometer, and with all human capacity till date, the drilling of the surface we have done, that is only 10 to 12 kilometers. 10 to 12 kilometers. Thus, the direct observation, this is possible only up to 10 to 12 kilometers, not beyond that. And as we know that the direct observation is always good, because it is the most authentic way to understand that what is going on in the interior and to answer all these questions and the doubts what we had while understanding about all these. So here we need to know that in the Earth's interior, how to enter, because the technological limit is there. We cannot send our sensors immediately to understand, to visit, to investigate in the interior beyond 10 to 12 kilometer. This is why we apply some other assets, some other methods to know about interior, and this method includes study of pressure. Before this, a study of temperature, and the study of density. Now, one by one, let us understand. A study of what is the meaning of study of temperature, a study of pressure, and what is the meaning of a study of density. A study of temperature. The study of temperature suggests that gradually we go deep inside. Gradually we go deep inside in the interior, then temperature increases. Temperature increases. Fine. And this increase in temperature is with the rate of 1 degree C per 32 meters. 1 degree C per 32 meters. What does it mean? We simply apply this, means what the information we have. Just let us apply this and you see that what temperature there could be in the interior. But before that, you can ask that how could we know that the temperature is increasing and with the rate of 1 degree C per 32 meter if we do not have any access directly into the interior. So there we know that we have the deep mines, and in the deep mines also, if we go deep inside, then the temperature increases. And as I had said that the mines we have now 8 to 10 to 12 kilometer deep. So we have very good idea that with every increasing depth, temperature increases with the rate of 1 degree C per 32 meters. All right. But here the catch is that we cannot simply keep on multiplying this. Fine. What does it mean? It means that if this is the rate of increase in temperature, it should be about 3 degrees C per 100 meters. Fine. Per 100 meters we can say. Now if it is 3 degrees C per 100 meters, it should be around 30 degrees C per 1 kilometer. So we can very simply say that at the depth of 6370 kilometer, the temperature should be 30 into 30, and that would be around you can say 2 lakh degrees C. 2 lakh degrees C approx. But this is not the right way. Why? Because the findings suggest that temperature increases with the rate of 1 degree C. Temperature increases with the rate of 1 degree C, true. 3 degree C per 100 meters, true. 30 degree C per kilometer, true. But only up to 8 kilometers from surface. Only up to 8 kilometers from surface. Beyond that, temperature does increase. Beyond 8 kilometer, temperature does increase, but with the reduced rate. It means the thermal gradient in the interior initially is very high with the increasing depth. But after 8 kilometer, the thermal gradient keep on increasing, but with the reduced rate. And this is why now we have concluded that in the interior at this depth 6370 kilometer, temperature should be around 4000 degrees C to 4500 degrees C. And sometimes you read that it is around 5000 degrees C. It is approx, it is not a very matter of discussion, 4 to 4500 or 5000 degrees C. This is the temperature in the interior. This is what we conclude. All right, means with the increasing depth, temperature increases, and this rate of increase in temperature is confined up to 1 degree C per 32 meter, up to the depth of 8 kilometer. Beyond that, temperature increases, but with the reduced rate, and that rate of increase in temperature finally leads us to the temperature of 4500 degrees C, 5000 degrees C. I hope it is clear. Now, if this is the thing, then obviously a very simple question arises from here, that this temperature, this high temperature comes from where? Means what is source of such a high heat, such a high temperature? So answer lies in number one, there is primitive heat trapped in interior since the beginning of Earth's formation. Primitive heat trapped in the interior since the beginning of Earth's formation. What does it mean? What does it mean? It simply means that, just imagine that when the number of those primitive objects, which were called planetesimals, were colliding randomly with each other. So because of that random collision, suppose if this one is hitting this one, suppose if this one is hitting this one, and each object is randomly moving, and that is why everything is hitting each other like this. So in that case, all these objects, now these are made up of iron, nickel, copper, silica, and various other things. So in this case, now all these are being hit. So that is why their temperature is also increasing. Their temperature is also increasing. Now, when all these things are combining together, and this combination or this combining process is due to the gravity. Fine, combined, and everything has combined together to form this earth. Suppose, then obviously now you can find initially every layer was very hot. Obviously every layer was very hot, but this hot layer would be hottest. This hot layer would be hottest in the central part maximum. All right. Then this part followed by that, this part followed by that, this part followed by that, or let me change the color. You will feel more comfortable. This part is there. Initially, this part is the hottest part. The surrounding part is less hotter but hotter. Then there is less hotter but hotter. And then there is least hotter but hotter. And now there is the blue part, suppose. So this blue part, which is the outermost layer, it will lose its heat easily. And here from here, loss of heat would be fastest. And this will leads to its solidification. And this solidification will lead to the formation of crust, let us say. So now this crustal part is there. This crustal part has completely solidified. Now this is there, solidified. But once it has solidified, now it will start acting as a lid, a cover, fine, upon the rest of the earth interior. And that is why it will not allow the heat from the interior to escape easily. All right. Now, if the heat from the interior has to escape out, then for that we need to pursue a volcanic activity or the volcanism. Now, this volcanism will do what? This volcanism will obviously erupt from here to every direction this way, and this eruption will obviously make give some ease to the interior, because eruption will come out with a lot of heat, sorry. And these eruptions will help in the cooling down of the interior. But even after 4.5 billion years, the Earth interior has not completely or sufficiently cooled down. The heat which was trapped those days during the formation process is still there, and this temperature or this heat is responsible for the high temperature interior has. It means that the Earth interior is gradually cooling down, but gradually cooling down. It is yet to cool down sufficiently. Since there is a lid of the hardcover lid upon the core, upon the surface, as we know, and since all of you have studied earlier that the crust part is solid, mantle part is solid, but the outer core is liquid. It means what? That if we have to make a comparison, then the crustal part should be the sufficiently colder part, mantle is bit, and then finally it is the outer core which is hotter than the mantle and the crust. So this is the reason why. I hope you got it. And this is the option number 1, means the not option number, point number 1, that the primitive heat trapped in the interior since the beginning of the Earth's formation. Now, scientists have concluded that it is true, the thing what I have given here and the geographers have given here, that is true. But because of this trapped heat, the temperature in the interior could be or should be around 1000 degrees C, not more than that. Temperature in the interior should be 1000 degrees C, not more than that. What does it mean? It means that if we concede that yes, the primitive heat is trapped in the interior and that is why temperature is so high, then such a high temperature will only be up to 1 degree C due to trapping of the ancient heat. But the temperature in the interior and especially in the core part, we have said it is around 5K. Fine. Then the difference is there of the 4000 degrees C. How come? How come is it possible? To answer this, the other argument comes, and the argument lies in that in asthenosphere or upper mantle, there is huge concentration of radioactive elements. Radioactive elements. And these are responsible for this. Now, when we say radioactive element, there is a huge concentration in the upper mantle. Then obviously, immediately, two questions come into our mind. Number one is, what are these elements? And second question is there, why does it is found in upper mantle mainly? Two questions come into mind. Now, here the answer is that the radioactive elements are those elements which have very high mass. Fine. Very high mass. If the high mass is there, their atomic weight is high, atomic number is also high, then due to the very high mass, these are mostly unstable. They become unstable. Unstable means because of their instability, it starts decaying. Decaying. Decaying means loss of energy. Fine. Good example of those radioactive elements, we can say that examples are there. Examples are there like uranium, like thorium, like plutonium, fine, etc. So these are those elements which have very high mass, which make them unstable, and they go through the process of decay. Fine. Now, this decay releases good amount of heat into the surrounding, and this surrounding heat is responsible for high temperature. High temperature. It is something we know about the nuclear energy. Fine. That also we will discuss in detail in upcoming classes in the paper 2. Paper 2 means, sorry, Indian geography. That nuclear energy is there. In the nuclear energy, we process nuclear fission. Fine. Nuclear fission is the process by using that we produce good amount of heat in nuclear power plants. Nuclear fission means when by breaking the nucleus of one atom into two. Similarly, on the sun, there is a process of nuclear fusion where the nucleus of two atoms combine together to form heavier atom like hydrogen, and hydrogen combine to form helium. And here on the nuclear power plants, we break uranium or thorium to produce heat. Now, here there is neither fusion nor the fission. It is simply the decay, and this decay produces good amount of heat. This good amount of heat is responsible for the temperature what we have. Because of this high temperature, there is the possibility of, if there is, then there is the possibility of nuclear fission. Never, ever of nuclear fusion in the Earth's interior. This heat is responsible for the high temperature what we witness in the interior apart from the trapped heat. I hope you got this answer. Now, the second question is there, why does it is found in the upper mantle mainly? A very simple thing is that during the process of the cooling, of the Earth interior, which is still going on, then initially when the number of planetesimals were colliding with each other, and because of that collision, high amount of heat was produced. But this high amount of heat, which had led to the partial melting of the Earth or the Earth interior, had led to a random movement of most of the elements and the most of the metals inside, most of the minerals inside. But gradually, when the process of cooling started, the materials started settling down according to their density. Fine. And the heavier metals settled deep inside, and the lighters one upon them. Then what the density of this uranium, thorium, potassium is there, it makes them settled in the upper part of mantle. Below to that upper part of mantle means the lower mantle or the outer core or in the inner core, the density of the material is higher than their density. And since these are heavier than the Cl and the aluminium, silica and the aluminium and silica and magnesium, this is why these are found in the upper part of mantle. I hope it is clear. If suppose it is not clear, then we can simply assume that, suppose if I have a glass of water, it is a bottle by the way, glass of water, and if I put some pebbles, small particles of rocks, some grains, some sand, and some very fine soil, and if I stir them. So now, if things are being stirred, water is being stirred, then everything will start moving this way. So what will you find that due to this force, everything, be it the pebble, be it the grains, be it the large sand particle or the small sand particle, will keep on moving randomly. But now if I leave this water still, this glass is still, then the gradually, according to their density, these will start settling down. The pebble will come in the bottom, then the large sand, then the grain, then the fine soil. This is the same thing what we have seen there in the course of history of the Earth interior. Initially, when things were moving randomly, at that time, due to high temperature, there was no stratification in the minerals. But in the latter stage, this kind of stratification took place, and that caused the settlement of the uranium and thorium at the at the layer of the upper mantle. I hope it is clear. Now, the third thing is there. That because of this, the high heat is there in the interior, or the high temperature is there in the interior. Third thing is there, that is transfer of gravity into, sorry, not transfer, conversion of gravity into heat. Conversion of gravity into heat. What is the meaning of conversion of gravity into heat? You know, with the increased mass of Earth, let me speak it again. Initially, when the materials which were combining together to form the Earth were relatively less in quantity, the size of the Earth was not as big as it is today. Mass of the Earth was not as big as it is today. And as per the Newton's law, gravity is directly proportional to mass. So over the years, when the most of the other things kept on joining, combining with the Earth, the mass of the Earth kept on increasing. And more the mass of the Earth was increasing, more the gravity was developing, and more the gravity was developing, it was also converting and creating heat. I hope it is clear. All right. Initially, mass of the Earth was not so high, then obviously the gravity was also not so high. And just to help you to recall, if you are not able to catch it, in the climatology, we will learn about the origin of atmosphere. And I'm sure that you have also studied this phenomena by yourself. This theory says that initially Earth had no atmosphere as such, and especially as thick as it is today. Because whichever the gases coming out from the interior of the Earth through the process of volcanism, Earth was not able to trap them. And these gases were simply escaping into the space. Do you have the answer that why is it so? Why those gases were easily escaping into the space and the Earth was not able to trap them? The answer lies in its gravity. The gravity of the Earth has not been always a constant value thing. Fine. Today, the Earth has the mass. This mass was not always there. Today, it is 5.5 gram cubic per centimeter. It was not earlier like this. It was lesser than. And if the mass was lesser, then obviously the gravity was also less. And if the gravity is less, it means the heat in the interior was also less. But gradually, if the gravity is increasing, if the mass is increasing, gravity will also increase. And if the gravity is increasing, then the substantial part of the gravity will also convert into heat, and that heat was responsible for increase in the temperature in the interior. I hope it is very simple, very easy. The further we can explain that with increasing depth, pressure increases. Pressure increases. And this increase in pressure is responsible for increase in temperature. I hope you will get this thing. Fine. Because what is pressure? What is pressure? The pressure, suppose if layer by layer, if thing is coming down this way, so every layer is increasing certain force per unit area, and that force per unit area will also increase that temperature in the interior. point. So these are the factors why temperature in the interior is high, and this temperature in the interior is increasing with the increasing depth. And finally, which starts with a very normal temperature, finally reaches to this temperature because of these factors. So this is the study of the temperature in the interior. And how can we conclude? We can conclude that temperature increases with increasing depth with the rate of 1 degree C per 32 meters and up to the depth of 8 kilometers. Up to the depth of 8 kilometers. Beyond that, temperature increases, but with relatively reduced rate. But finally, at the depth of Earth's core, temperature reaches up to 5,000 degrees C. 5,000 degrees C. Causes of such a high temperature are: number one, trapped heat in the interior. Since the formation of Earth. Number two, presence of radioactive elements. In upper mantle. Its decay process produces heat. Number three, conversion of gravity into heat. Conversion of gravity into heat. So they will give you options like this, that why the heat is in the interior is high, what is the temperature. So the options will be coming this way. You can easily answer them. Now, as we had discussed, so this part is done. Now come to the pressure part. Now what the pressure says? Pressure says that, what is pressure? As I simply said, that suppose if this is the interior and this is the radius r, then with increasing depth, you can see layer by layer, pressure would be increasing. This is increase in pressure. And what is pressure? As I said, so pressure is actually force per unit area. It is force per unit area. So if it is force per unit area, then suppose if I am standing over here then on the floor I am exerting certain amount of pressure. है ना? Now, if someone is coming upon me, then the pressure will increase not only upon my shoulders, but also upon the surface I am standing. And gradually, if the person by person, if the people are coming and joining this pyramid, then finally the force per unit area we all would be exerting on the surface would be high. This is the simple phenomena, and this is called the force per unit area, and this is called the pressure. Now, what does it say? And what is its use? It says that at the temperature of, as we have seen here, the temperature is 5000 degrees C. Don't you see, don't you think that this temperature is actually disturbing? Why disturbing? Why disturbing? Because at such a high temperature, rocks should melt down. Rocks should melt down. The interior of the earth, especially this part and this part, it should be in the liquid state. So should we conclude that the earth interior is in the liquid state? Do not jump any conclusion. You simply think that is it possible to say that in the earth interior temperature is high, so high, and that is why the rocks should be in the liquid state? Yes, we can say that. So do we want to say, because the melting point of the iron is 1000 degrees C, and this 1000 degrees C we can reach at the very shallow depth. Fine, you can say hardly 100 kilometer or 200 kilometer. So is it possible that the entire earth interior from that beyond the depth of 100 kilometer is around, or 200 kilometer is in the liquid state? Yes, if we allow the temperature alone to play significant role, then we should say yes, it should be there. But that is not the fact. Why? The reason is pressure comes into the role. Pressure actually does two things. Number one is there, as I said, that pressure also increases temperature. So this is what the one aspect that I have already given to you. But the second aspect is there, that with the increasing pressure also increases melting point of the rock. Melting point of the rock. What does it mean? In a very simple way, I will explain. Suppose if iron melting point is 1000 degrees C, fine, in free air, in free atmosphere. All right. Then the same iron will now melt upon 1200 degrees C or 1500 degrees C in atmosphere with high pressure. With high pressure. Up iron which is melting on 1000 degrees C and now it is melting on 1200 degrees C or the 1500 degrees C, depending upon what amount of pressure we have exerted upon. So it suggests that since the pressure has increased from here to here, because of this, the melting point of the iron has also increased. Now, if we apply this formula on the previous part, there we had said that the rocks in the interior should be in the molten state. Why molten state? Because of the very high temperature, and that is why it should be liquid. It will not be a liquid one because of the high pressure also, which has increased its melting point. I hope it is clear. Fine. Temperature is increasing, reaching up to 5K. Degree C, that could have melted the rock, but the rock is not melting because of the high pressure. Clear? High pressure. So we can conclude now, you can note down, we can conclude now with increasing depth, pressure increases. Pressure is force per unit area. Pressure is force per unit area. Per unit area. With increase in the pressure, number A, temperature in the interior increases. Number 2, melting point of the rock also increases. Since melting point of the rock increases, this is why Earth's interior behaves. This is why Earth's interior behaves like a solid sphere, even at such a high temperature. High temperature. High temperature. Is it clear? But here there is one more catch. Now it says that with increasing depth, pressure increases, that increases the melting point. Agreed. Agreed. Beautifully agreed. And it is giving a very good insight also. But at the same time, there is a problem, and that we also need to understand, that there is a concept of critical limit. There is a concept of critical limit. And that is applied on almost everything. Critical limit concept says that with the increase in the pressure, melting point increases. Agreed. But there must be a certain limit. There must be a certain limit. Certain limit in the sense that if the pressure is increasing and the melting point is increasing, then it will increase, melting point will increase only up to a certain degree. It is not the case that melting point will also keep on increasing with an amount of pressure if we are increasing. No. No matter what amount of pressure we will exert upon the surface, beyond that critical limit, melting point of the rock will not increase. All right. Melting point of the rock will not increase. You see, very carefully I have said, if the melting point is 1000 degrees C, we can increase it up to 1200 or say the 1500, but it will not reach up to 5K, 5000 degrees C. So how come Earth interior is able to maintain that solid state at such a great depth and at such a high temperature? Then obviously the answer doesn't lie in the explanation of the pressure alone. Pressure does play important role. It's true. But it plays important role only up to a certain limit. Beyond that limit, no matter what amount of pressure we will increase, the melting point of the rock will not increase. And for this, the third thing comes into the scene, and that is a study of the density. Now, what is the meaning of density? When we say density talks about the mass. Fine, mass. So suppose, just take one example. If we have 1 kg of iron and 1 kg of cotton, fine, and if we put them on a weighing machine, it is 1 kg iron and it is 1 kg cotton. Now, on the weighing machine, which would be heavier? So very obviously you would be laughing, that's a 1 kg this iron and the 1 kg cotton, they both have the same weight. The weighing machine would be showing the same figure. True. But here you can see the cotton has such a large volume and the iron has less volume. Fine. It is bulky, it will cover more area on the surface as well as in the air, and it is less bulky, it will cover less area. So iron is less bulky, cotton is more, it is more voluminous, it is less voluminous. It means what? Its density is high. Density is high and its density is less. Now we are saying that if we exert pressure upon it, then its volume will decrease, will come up to here. If the volume is decreasing, it means what? The molecules of the cotton will come close to each other, and we are saying it will make it more denser. True. This more denser will increase the melting point. True. But can we change this cotton into the iron just by increasing the pressure? Very simple answer is no. If that was the case, then for that we do not need to go for the iron ore mining. And just take any substance and keep on increasing the pressure and change them into the iron. But we know that high amount of pressure which converts the simple elements into such a high density elements like iron, we cannot produce on Earth. This iron is produced in the big stars and comes out from those stars through the process of supernova explosion. So what the Earth interior has, that has a very high density, and that high density is not there only because of pressure. Pressure, as I said, plays a role, but also because nature has made them of high density. Nature has made them of high density. Nature has made iron. Nature has made iron. Nature had made nickel. Nature has made silica. Nature has made aluminium. Nature has made silica, magnesium, etc. All those things nature has made. These are not changing their state because of the pressure. Pressure plays an important role, but only up to the certain limit. All right. So it is said that the Earth interior is made up of high density rocks or the density materials. Now it means, can we conclude that gradually we are going deep inside, density also increases? You can make the argument that sir, we understood this thing that at the core pressure is high and the density of the rock should also be high because of this and this reason what you have spoken about. But at the same time, how can we make the conclusion that yes, in the interior, yes, the materials are of high density? Did you get the catch? You see, the question is that the logic suggests that the pressure is high and the interior is high. But how can we conclude that in the core also the density of the rock is high, density of the medium is high? Do we have any such kind of calculation, or it is simply based upon the assumption? So here assumption as well as the calculation both support this idea. How come? The surface rock, the surface rock is there, which we can easily find on the surface. It has the density of 2.6 gram cubic per centimeter. All right. And it varies from 2.6 gram cubic per centimeter through centimeter to, to 3 gram cubic per centimeter. Fine. If suppose if the earth is a very homogeneous thing and there is no difference in the density, then the average density of the earth should be somewhere close to 2.63, 3.5, like this. But it clearly, the satellite study suggests that the average density of the earth is more than 5.5 gram cubic per centimeter. Then how will you make this compensation? This compensation means the gap between the 2.6 or 3 to 5.5, you can fill this gap, you can compensate this gap only by deriving a conclusion that in the interior, the density should be very high, and it should be around 11 to 13 gram cubic per centimeter to fill this gap. And obviously, this 11 to 13 gram cubic per centimeter will not come immediately or automatically with a leap or jump. It must be increasing with increasing depth. Clear? So, this is the study conclusion of the temperature, pressure, and the density. And if in one line we have to conclude, we can say that with increasing depth, temperature increases, pressure increases, and density also increases. All right. Now, I hope you have understood this thing. You can note down finally. With increasing depth, density of the rock increases because rocks in the interior are made up of high density. On the surface, density is only 2.6 gram cubic per centimeter to 3.0 gram cubic per centimeter but the average density of the earth by using satellites comes as 5.5 gram 5.5 gram cubic per centimeter, and little more, and little more. It clearly indicates that the Earth's interior has relatively very high density, than the rocks found on the surface. And the density should be approximately 11.0 gram cubic per centimeter, 11.0 gram cubic per centimeter to 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 13 gram 13.0 gram cubic per centimeter. Clear? But now, this study of the temperature, pressure, and the density has a limitation. Of course, these have given a very outstanding information about the interior, but these have some sort of, haziness. Haziness in the sense that we are not getting all the information with all clarity we were looking for. Like, temperature increases, pressure increases, density increases, but what is the behavior of the rock? If it is in the solid state, if it is in the liquid state, or somewhere gaseous atmosphere is there, we cannot either affirm or rule out clearly. Fine. There is that hazy atmosphere. This is why we think about other options available to us. And this other option is a study of meteorites. As we know that the meteorites are those objects which enter into the Earth's atmosphere time to time, into Earth's time to time, because these are the near Earth objects which enter due to the Earth's gravity, and majority of them are completely burnt. Fine, but few of them which have some residue body and good mass, they are able to cross the atmosphere and reach on the surface, hit the surface as a solid body. Now, it is said that the process of formation of these meteors was very much similar to the formation of the Earth. So, the study of the geology of these rocks can help us in understanding about in developing understanding about the Earth's interior. True, it is true that the process of the formation of this solar system had taken place almost the same process and the same time frame. And it also suggests that the meteors have their body mainly made up of iron and nickel. Remember that this finding is actually main reason why we suggest that the core of the Earth should be made up of iron and nickel. One important reason is this one also. But the problem is, it is true that it is giving us a good idea. It is true that the process of the formation was the same. It is true that perhaps Earth's interior is made up of iron and nickel. But you know that the Earth has the radius of 6370 kilometer. And such a high radius of 6370 kilometer is responsible for all those differences in the pressure, temperature, and the density what we have just talked about. Here, meteors have the maximum size of few hundred kgs. And you know that it is a size that brings most of the changes, most of the differences in the interior. Because of the size of the Jupiter, because of the size of the Mars, because of the size of the Earth, there are the differences in these planets also. Thus, to say that the meteors are a very good indicator or a very good evidence to suggest that what kind of interior there should be, it would not be a very wise way to conclude. So geologists do believe that the meteors should be studied, but it has these limitations. All right. In one line, you can simply write, meteors give a good indication that the Earth interior should be rich in iron and nickel. All right. Now, the third one is, sorry, my fifth one is a study of volcanoes or volcanic eruption. What is volcanic eruption and how does it take place? We will study in detail in the upcoming chapters. You need not to worry about volcano. But a very simple meaning that you can infer from the term volcanic activity, that it is an opening on the Earth's surface through which Earth vomits out its heat, extra heat, time to time. All right. But whenever this heat comes out, it suggests that there is a molten rock. There is a molten rock. All right. And if there is a molten rock, so that is called magma. Magma beneath surface. Beneath surface, and it is called lava on the surface. All right. Number two is there that magma, or say lava, magma comes out with burst, especially you can say, especially in central eruption, especially in central eruption. And thirdly, density of magma is greater than rock density we find on surface. We find on surface. Three things are there. That magma is molten. Magma is molten. This molten thing suggests what? That the temperature is high. The same conclusion that we had drawn. Magma comes out with a burst. It means what? Pressure is high. The same conclusion. And density is high. Means same conclusion. So actually, a study of volcanic eruption gives us a sort of assurance that what the study we have made till now is not a wastage of time either. Fine. It is a very fruitful time. The time we enjoyed in making the study of the interior by studying temperature, pressure, and the density, as well as the study we made of the meteors. There we said that yes, it should be made up of iron and nickel. So all these findings are in a very right direction. Fine. So for that, we should be thankful to the study of volcano. But this volcanic study also has a limitation, and the limitation is there that the maximum depth from where this molten magma can reach is 700 kilometer. Fine. In case of volcanoes related to plate tectonics, and the maximum depth it could have of 2900 kilometer. Fine. In case of hot spot volcanoes, or that is also called mantle plume. Mantle plume. So you can see that this one, you can see that the 700 kilometer or the 2900 kilometer is not the sufficient depth or the only depth we were looking for. It gives us a very clear indication that yes, up to the 700 kilometer, this kind of the mineral composition is there. You can ask me that, sir, how are you concluding that up to this depth, what is the mineral composition? Very simple thing is that if the magma is coming out from the depth of 700 kilometer, then the magma is not something, a liquid which is stored over there. Fine. It is also being formed continuously, and it is being formed because the rocks of the nearby region are melting down due to XYZ reason. We will discuss later on. So if it is melting down, so that melting of the rock will also get the same chemical composition the surrounding rocks do have. And then if it is coming through, so it is not coming through a closed system. It is coming through a process of, remelting and remelting of the rocks of the medium through which it is rising up. It means the chemical composition will also change of the magma between the source of the big source of the magma as well as the destination, and it will be carrying every chemical thing whichever it will come into its path. So if the depth is 2900 kilometer, up to that we can figure out what is the chemical composition. And if the depth is 700 kilometer, up to that we can figure out what is the chemical composition. I hope now you are able to infer the entire thing. So this way, it gives us a very good information, very substantial, and you can say that it must be appreciated. But at the same time, the limitation lies in that the depth is only 2900 kilometer at the max. And if the depth is only up to 2900 kilometer, then still there is a gap 6370 into 2900 kilometers. Almost. It means we still need to know 3000 plus kilometer. What is there inside? And we have exhausted our most of the options. All right. You can note down so that we will move to the next evidence. Volcanic eruption gives us a good idea up to a depth of 700 kilometer, up to a depth of 700 kilometer, or maximum up to the depth of 2900 kilometers, under bracket in case of hot spot volcano, in case of hot spot volcano. But still a very large area, that is the area of more than 3000 kilometer, remains unexplored, remains unexplored. Secondly, volcanic eruption reveals some secrets about eruptions, reveal some secrets about the chemical composition of the medium, chemical composition of the medium, but it does not give clarity, but it does not give clarity on the stratification, on the stratification, comma, heterogeneous layers of the interior. Now, we reach to the study of seismic waves. The study of seismic waves. Before I start this, I want to let you know that the study of seismic wave is considered as most comprehensive, authentic method of developing understanding because of its accuracy. And secondly, it is the only agent or the method through which we can peep inside deep into the interior of Earth. Fine. But first of all, and see, in exam also you can expect the question from this part more than the others. However, question can come from the any part. When we talk about seismic waves, the very simple thing is, what are seismic waves? In detail we will discuss later, but just to understand. Here, suppose there is a medium. It is A, B, C, and D. A rock it is. rock medium is there. Fine. Now, if any external force is applied upon this, suppose it is my hand. Fine. If a force is applied upon this force will pass through the medium of the rock, in the form of wave, because every energy flows in the form of wave. Now, if this wave is moving from here to there, fine, then obviously this rocky medium has A, B, C, and D. Why I have given this kind of blocking? Because if the force is not sufficient, then the medium A would exert some resistance and my force would be consumed there only. All right. If it is little more, then it will not be able to pass through the resistance exerted by B, by C, by D, and so on. But if the force is sufficient, then in that case, what will happen? In that case, the force will pass through the medium of A, B, C, and D. And in this process, the particles, the molecules of A, B, and C will be exerting the resistance and will be releasing the resistance exerted by releasing the force exerted by the wave. Now, in this process, they will start vibrating on their place. This deep vibration, deep shaking in the surface is called earthquake, and wave is called seismic wave. I hope it is clear. And now, where the force is applied first, which is changing place from where what is this force? Means rocks have the kinetic energy, potential energy. That potential energy is being converted into the wave or into the kinetic energy, and the kinetic energy is flowing in the form of wave. All right, the place from where potential energy is changing into kinetic first is called focus. All right, and this focus is mostly beneath the surface. I hope it is clear. Just let me give you a better diagram. Let's suppose this is Earth surface, Earth interior, and this is the point from where it is changing into kinetic. It is called focus. All right, beneath the surface mostly. Now, obviously, if this is the point focus from where potential energy is converting into kinetic energy first. All right. Then this energy in the form of seismic wave will flow into every direction. Fine. Every direction, and this direction would be like this, like this. You can find that this place at the top is something which is closest to the focus. It is closest to the focus. That is why it is called epicenter, and that is always on surface. It is always on surface. This much we have discussed. Now, here you see, if energy is being produced, means the potential is being energy is not produced at all. Energy is neither created nor destroyed. So if potential energy is changing into the kinetic energy, then in that case what will happen? It is, as I said, that it will start flowing in the form of wave, and that is called seismic wave. Now this is seismic wave flows in the form of two waves. One is called surface wave and other is called body wave. Surface wave is of two types, that is called the L wave and that is called R wave, and the body wave is of two types, that is called primary wave and secondary wave. Primary wave is also called P wave and the secondary wave is also called S wave. L wave is also called Love wave and the R wave is also called Rayleigh wave. Since the surface wave do not play any role in gathering information about the interior, that is why we will not talk about them here, but we will talk about them in detail in the chapter of earthquake. All right. Now, P wave and the secondary wave. P wave and the secondary wave are those waves which move across the interior of Earth. It means the yellow lines are actually showing that how this entire P wave and the S wave will propagate. So suppose from the focus is there, and if the P wave and the S wave have to propagate in all the directions, so here what will reach? P and S. Here what will reach? P and S. 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 P and S, P and S, P and S, P and S, P and S. In all directions, P and S is reaching. But here at the bottom, it is P, it is P, it is P, it is P. There is no S. Now, this difference leaves us into a situation where we need to understand that why P and S waves are not reaching over there. Let me make the things simpler. What actually we are trying to do? We have fixed number of seismograph machines all across the globe, and we are trying to track down any sort of deep sinking that is taking place on the Earth's surface or in the Earth's surface. And as the energy is neither created nor destroyed, so we are assuming that if any earthquake of high magnitude comes over here, then the waves must travel in all the directions on the surface, and everywhere they will reach. Of course, the intensity or the magnitude of the wave will come down, but the wave will reach. And if the wave is not reaching, it means the Earth interior had some such secrets about which we are not aware of. All right. Now let me rephrase this entire thing. Earth interior, suppose if it has the homogeneous body, there is no difference at all. There is nothing to surprise us. Then the P and S wave should reach there. But since if the P wave is reaching over here, not the S wave, so there must be something. Now, why there must be something? Because we know that there is a difference in the property of the P wave and the S wave itself. What is that difference? What is that difference you see? Actually, when we talk about the P wave and S wave, so there we need to understand certain things. P wave is there, that is have maximum velocity S wave have lesser velocity than P. Than P. Has shortest wavelength have longer wavelength than P. Than P. Refracts when medium is changed. It also refracts when medium is changed. Medium is changed. Can travel through all mediums, that is solid, liquid, and gas. And gas. It can travel only through only through solid medium. Now, these are the different properties of the P wave and the S wave. Different properties of the P wave and the S wave. It seems to be very simple difference when we are about this one, and to some extent this one also. But the bigger difference lies in that S wave cannot travel in all the mediums, unlike P wave, and the P wave is able to travel through solid, liquid and the gas. Fine. Refraction and this, if we take 2 points together, then we are able to reach up to some conclusions. Fine. And the conclusions are here, as you can see. As you can see this diagram. What actually it is suggesting to us? It is suggesting that, number one, this line could have been this way also, this way also, this way also. But you see, this is not a straight line. And it has some curvature and curvature all across. This curvature is because of this refraction property of both. Since both are refracting when the medium is changed. Medium is changed. Refraction means what? If I put this pen into this water, or you can try at home. If you put this pen into this water, this pen will look like tilted. Fine, a little thicker. Why is it so? The reason is that refraction. Fine. So refraction is actually property in physics. I hope that you people have studied in the class 9th or 10th. It is not a big deal. You have not to worry about too much. So there you see that it is refracting. And secondly, the second important thing is that only P and P is reaching over here. It means what? If the P, S and S is reaching over here, both are reaching over here, it suggests that the medium has the difference in the density, but overall it is homogeneous. Now, what does it mean? Difference in the density but the homogeneous? Because this pen is solid, this bottle is solid, and the iron is also solid. So it remains a solid medium, but there is a difference between the iron and this plastic. So with the increasing depth, density is increasing, solidity is increasing, but at the same time it remains a solid one. But somewhere the problem lies in the middle. Here somewhere there is a medium that is actually a liquid medium. Why are we saying liquid? Because S wave cannot pass through the liquid medium. That is why only P and P is reaching over there. And secondly, since there is a huge difference in the medium, means solid to liquid, this is the reason why P wave was supposed to reach over here. Reach over here at least. But even the P wave could not reach because it was heavily refracted. I hope you are getting this, the meaning of the refraction. Because of this refraction, this zone and this zone is called shadow zone of the P. It is called shadow zone of P wave. This is called shadow zone of P wave. This shadow zone of P wave lies between 105 degree from focus to 145 degree from focus. And this side also 105 degree from focus to 145 degree from focus. Clear? But if we talk about the shadow zone of the S wave, so this goes from here to here. This is called shadow zone of S wave, and that is from 105 degree from focus and beyond. Clear? Now, what can we conclude? We can conclude that at least 2-3 things immediately, that the Earth interior is not homogeneous. Apart from those temperature and the pressure and the study of meteorites and the volcanoes, etc., by making the use of the information we gather by reading seismic waves, we can say that the Earth interior is not homogeneous, it is heterogeneous. At least 2 zones are there. That is, one is the solid and other one is the liquid. Fine. And this is why S wave is not able to propagate through the central medium of the interior. But is it conclusive? Or do you really think that there is no other possible information laying in the interior, or the interior is still trying to hide something? If it is so, then to your surprise, number of other informations and the concrete informations are yet to come. And these informations I will share with you in tomorrow's class, in the next class. So just try to revise this, memorize this. And yes, many of the questions what they have asked from the Earth interior chapter, you can try to solve. And I'm very sure that you will be very comfortable. I will make you more comfortable, and I will make you more confident in the next video when I will conclude this chapter and start the new one. In this session, this much I had to say. Let me shine off. Neeraj Bhardwaj, Drishti IAS. Thank you very much.